Hello everyone. So in today's video, we are going to go over this paper titled BitFit, Simple Parameter Efficient Fine-Tuning for Transformer-Based Mass Language Models. So I came across this paper when I was going through another paper on skill neurons, and this paper was referred to in one of the experiments. Alright, so this paper is by Elad Ben Zakien, Shorley Rav and Yoav Goldberg. I'm really sorry if I mispronounced any of those names. So for the abstract, they introduced BitFit. BitFit is a sparse, fine-tuning method where only the biased terms of the model or a subset of them are being modified. So traditionally in fine-tuning, you freeze, say most of the layers and only allow a layer to be trained and so on. In their case, they are only fine-tuning the biased terms. They show that with small to medium training data, applying BitFit on a pre-trained BERT is competitive and sometimes even better than fine-tuning the entire model. And you might guess that this is very efficient because there are very less bias parameters as compared to say freezing and training an entire layer only. So for larger data, the method is competitive with other sparse fine-tuning methods. Sparse fine-tuning method being methods which only fine-tune a subset of the parameters. Besides their practical utility, these findings are relevant for the question of understanding the commonly used process of fine-tuning. They support the hypothesis that fine-tuning is mainly about exposing knowledge induced by language modeling training rather than learning new task-specific linguistic knowledge. So essentially, you already know that your language model has learned a lot of stuff, right? You just want to make that more or promote that more for a specific task rather than teaching it a lot about that task. All right, so for introduction, large pre-trained transformer-based language models, and in particular bidirectional mass language models like BERT, are responsible for many significant gains, of course. Under the common paradigm, the model is pre-trained on large annotated corpora with the LM objective and then fine-tuned on task-specific supervised data. So this is the traditional format. You say take a BERT model and then fine tune it for sentiment classification. The large size of these models make them expensive to train and more importantly expensive to deploy. This, along with theoretical questions on the extent to which fine tuning must change the original model, has led researchers to variants of fine tuning where one identifies a small subset of the model's parameters which need to be changed for all good performance in end tasks while keeping all the others intact. So they present a simple and effective approach to fine tuning, which has the following benefits. So, changing very few parameters per fine tuned task, and then changing the same set of parameters for every task, which would be task invariance, and then changing the change parameters are both isolated and localized across the entire parameter space. And for small to medium training data, changing only these parameters reaches the same task accuracy as full fine tuning and sometimes improves the results. So, why are these important? We'll go over them one by one. uh, unless they are going over that in the future. I'll just give a brief idea about why these are important. So you want to make the fine tuning more efficient. So you want fewer parameters to get the same results. You want it to be task invariant because you don't want to find those set of parameters again and again because finding those parameters is already very expensive. So if you find, okay, these 10 or say 100 parameters are what are good for every task or give good, reasonable performance in every task, you wouldn't mind using them. Then the change parameters are both isolated and localized across the entire parameter space, so they are not like very concentrated in one layer, I guess. And for small to medium training data, of course, for large training data, when you have a lot of data, your model uh, needs more memory or bandwidth to learn them, right? And constraining the model would, of course, hamper. But for small to medium training data, you really want to get similar or even better performance. And for large, you wouldn't mind maybe losing a bit. Specifically, they show that freezing most of the network and fine tuning only the bias terms is surprisingly effective. Moreover, if we allow the task to suffer a small degradation in performance, we can fine tune only two bias components, the query and the middle MLP bias terms, amounting to half of the bias parameters in the model and only 0.04% of all model parameters. So the bias in the query is the bias in the query matrix, which, if you remember back from attention, you project your input into query key and value, right? So the bias associated with the query and the middle of the MLP bias terms are so you have a feed-forward network in the every encoder block. So the bias terms in the middle of that. This result has a large practical utility in deploying multitask fine-tuned models in memory-constrained environments, as well as opens the way to trainable hardware implementation in which most of the parameters are fixed. Additionally, it opens up a set of research direction regarding the role of bias terms in pre-trained networks and the dynamics of the fine-tuning process. Alright, so background, fine-tuning and parameter-efficient fine-tuning. So in transfer learning via model fine-tuning, a pre-trained encoder network takes the input and produces contextualized representations. I assume if you're reading, following along this paper, you already know this stuff. Then a task-specific classification layer, which they are considering linear classifier, is added to the top of the encoder, and the entire network is trained end-to-end to minimize the task loss. So this is your traditional setup. You have this encoder stuff, and then you have this task specific linear classifier. So you might have a few layers of MLB, and then you have a softmax over say 4 values. So you go from here to here and then here to here. And this is not like one standard way. You can have multiple ways. You might not even train everything. You might only train some encoders and so on. So desired properties, while fine-tuning per task is very effective, it also results in a unique large model for every pre-trained task, making it harder to reason about what was changed in the fine-tuning process, as well as hard to deploy, especially as the number of tasks increases. Uh, yeah, because if you have a change in a lot of parameters, you don't know which one is affecting it the most. So ideally, you would want the results to match of a fully fine-tuned model, change only a subset, enable tasks to arrive in a stream instead of requiring simultaneous access to all datasets, and the set of parameters that change value is consistent across different tasks. So learning versus exposing. So the feasibility of fulfilling the above requirements depends on a fundamental question regarding the nature of the fine-tuning process. So to what extent does the fine-tuning process induce the learning of new capabilities versus exposing the existing capabilities of language models. So since so some models are being claimed to have seen almost all of the internet, right? So they must have seen a lot of data sets which we are using for downstream tasks or fine tuning already in their data, right? You just want to uh, fe- fetch that specific uh, memory or that specific skill set of the model for the task. So for existing approaches, you have two recent works. The first work is by Holsby et al. 2019, where they have adapters. So they achieved the goal by injecting small, trainable, task-specific adapter modules between the layers of the pre-trained model, where the original parameters are shared between tasks. And the second is by Gu et al., which is diffuse diff pruning, which achieves the same goal by adding a sparse task-specific difference vector to the original parameters, which remains fixed and are shared between tasks. The difference vector is regularized to be sparse. And both methods allow adding only a small number of trainable parameters per task, and each task can be added without revisiting previous ones. So these were the second and third criteria, but they also fail in some cases. So for the class one, they partially fulfill it, and because they suffer only a small drop in performance due to when compared to full fine tuning, and the adapter method does not, but not the diff pruning method also supports criteria for. So in diff pruning, even though it's more parameter efficient than the adapter method because it adds no new parameters as compared to adapter method which is adding layers, it is not satisfying criteria 4. And if we go back, criteria 4 was the set of parameters that change value is consistent across different tasks, but here we don't really achieve that. And if we compare diff pruning and adapters, we show that We perform favorably on many tasks while also satisfying the criteria for. So that this is where BitFit comes in. So bias term fine tuning, BitFit. So in this, they freeze most of the transformer encoder parameters and train only the bias terms and the task specific classification layer. So BitFit has three key properties. It matches the results of fully fine-tuned models, enable tasks to arrive in a stream, and does not require simultaneous access, and fine-tune only a small proportion of the model's parameters. So this approach is parameter efficient. Each new task requires storing only the bias term parameter vectors, which accounts to less than 0.1% of the total number of parameters, because the remaining model is same, right? If you want to save your model, say you have 10 different tasks and you want to save your a different model for every task. 99.9% of the model is same, so you can say keep one copy of BERT and then keep a copy of only what were the bias values for task A, task B, task C, and when you want to do a particular task, you can just retrieve the two values, so one from the original BERT model and the bias values from your task specific storage. So each new task again requires only amounts less than 0.1% of the total number of parameters in the task-specific final linear classification layer. Concretely, the bot encoder is composed of L layers, where each layer L starts with M self-attention heads, where a self-attention head, so M comma L, has a key query and value encoder, each taking the form of a linear layer. So again, as we discussed, you have the projection and then you have a bias term being added. So this is the bias term which they augment. And similarly, if you have this for key and value as well. So X is the output of the former encoder layer. So you in the first layer, this would just be the embedding layer's output. But for say the second encoder layer, this would be the output of the first encoder layer. These are then combined using an attention mechanism, and the attention mechanism does not have any parameters. So this gives you the hidden state. And then finally, this hidden state goes into the perceptron, where you have uh, dropout, then you have layer normalization, then you have Galileo activation, again dropout, and then again, I guess this is layer normalization once again. And the collection of all the matrices of this form and vectors of these form indicated in blue and purple are the network parameters, and the purple ones are the bias terms. So I hope that makes sense now. The bias terms are additive and correspond to a very small fraction of the network. Additive meaning they are only being added, they are never being multiplied or something like that. In BERT base and BERT large, these are only 0.009% and 0.008% of the total parameters in each model. They show that freezing all parameters and fine-tuning only the additive bias terms, they achieve transfer learning performance which is comparable and sometimes better than fine-tuning on the entire network. So they are freezing everything and then fine-tuning only the additive bias terms. So W and G, if you go back, W were the matrices and G were the parameters for the layer normalization. And they also show that they can fine-tune only a subset of the bias parameters, namely those associated with the query and the second MLP layer. So only BQ and BM2. So going back once again, this is BQ and BM2 is this feed forward layer, so the second feed forward layer. I should uh, make the arrow a bit far away so that it does not hamper the superscript. So for the experiments, they took the glue benchmark consistent with previous work. They exclude the WNLI tasks on which BERT model do not perform the majority baseline. Alright. So for model optimization, they use BERT base, BERT large, and Roberta base using the Hugging Face implementation. So in the first experiment, they compare BitFit to diff pruning and adapter method. So table 1 shows the dev set and tested performance. The experiments used the BERT large model. On validation set, BitFit outperforms diff pruning on 4 out of the 9 tasks while using 6x fewer trainable parameters. As for test result, two clear winners wins compared to BitFit and 4 clear wins compared to adapters while using 45x fewer training parameters. So if we go back here, so the first row is of course full fine tuning. Then you have diff prune versus BitFit. So V is the validation set and T is the test set. So for validation set, these are the specific tasks for which BitFit is better. I should zoom in a bit so that I don't accidentally highlight the wrong part. Also this, and then for the test set again, BitFit is better in some of the tasks. So BitFit is better in two tasks as compared to both of them. But if you just compare pairwise, you can see in some tasks it is better. So in the QNLI task, BitFit is better than adapters, but not better than diffprone and so on. So different base model, they repeat the BERT large results on different base models. So BERT base and Robota base. The results in table 2 show that the trends remain the same. So table 2 is here, and you can see this is for BERT base and BERT large and Robota. Are the bias parameters special? So would this be true if you just take a similar number of parameters from the entire model instead of just taking the bias parameters? So to do that, they randomly sampled the same amount of parameters as in BitFit from the entire model and fine-tuned only them, which is rand uniform. The results are substantially worse across all tasks. Similar patterns are observed when the random parameters are sampled as complete rows in the parameter matrices, which would be rand row or column in table 3. So going back once again, these two are the random baselines, and if you can see, these values are significantly lower than what BitFit achieves. So 90.2 versus 87 and 88. So these the other three rows in purple we'll get to them in the further sections. So can we fine tune on only a subset of the bias parameters? So already we are using very few parameters. Can we go even further? So they define the change in a bias vector to be this. That is the average absolute change across its dimensions between the initial and the final. So figure 1 shows the change per bias term and its fine-tuned value per bias term and layer. For the RTE task, other tasks look very similar. So we'll maybe go over the appendix. So this is figure 1, right? So for layer 1, this looks a bit messed up because OneNote apparently just destroys PDFs when loading them. But I can try showing you the accurate results. Uh, by accurate, I mean just a more clearer version of these. Okay, these are already quite distorted. So you can see this is the query, this is the second multi-layer perceptron bias, and then you have the third one, then you have layer normalization ones, and so on. And these are distributed across layers. So you can see there's a very high concentration across on the query in the second M2 layer. Right. So the key bias has zero change. Uh, in contrast, the bias of the query and the bias of M2 intermediate MLP layer changes the most. So this is consistent with the theoretical observations that the key does not change much by Cordonier et al. I'm not familiar with this work, but they're reporting that this has already been studied before. They again fine tune only these two parameters, and results are only marginally lower than fine tuning all the bias parameters. So tuning either alone yields substantially worse results, so indicating both of these bias are essential. And as expected, using a frozen BERT-based model yields much worse results because you're not training anything apart from the classification head, I guess. So they haven't really defined what all they've frozen. If they freeze the classification layer as well, then there's no training, right? So I guess They're freezing everything apart from the head they add. So, right, if you can see, this is not too shabby, just fine-tuning these values. It's in a 1% range in most cases, but taking them alone results in severe degradation. So maybe these two together interplay a lot. Then result generalization gap. While in most cases full fine-tuning reaches near 100% train accuracy, we find the generalization gap, the difference between training and test error, is substantially smaller for the BitFit model. So this is again a good thing. For token level tasks, the glue tasks are all sentence level. We also experimented with token level, so pen, tree bank, post tagging tasks. Full FT results for Beard base, Bert large, and Robota base are 97.2, 97.4, and 97.2, while BitFit is almost the same. So for two of them, it's the same, but for one, it is zero point 0.1 lower. Then for the size of the training data, how does that affect? So the glow results suggest a reverse correlation between the BitFit ability to reach full FT performance and the training set size. So to test this and to validate another token level task, they took Squad version 1. The results are shown. So BitFit dominates over full FT in smaller data regime, while the trend is reversed while the training data is available. They conclude that BitFit is a worthwhile targeted fine-tuning method in small to medium task regimes. So you can see the takeover starts from somewhere around here, which is around 7,000 to 8,000 samples. So a lot of tasks, especially say tasks concerning hate speech and some other uh, more nuanced tasks don't have a lot of data for some specific tasks, not all the tasks, but some tasks in hate speech detection. So this might be very helpful there. Then related works. The problem of identifying the minimal set of parameters to achieve good performance has been studied before. This is related to model compression and also to the more fundamental question on the nature of pre-training and fine-tuning process, the linguistic knowledge induced by each of them, and the extent to which it generalizes to different tasks. So you have over-parameterization. Large language models were shown to be over-parameterized. They contain more parameters than needed in inference. So Gordon et al. Demonstrated that over-parameterization can be exploited in fine-tuning. Pruned networks perform well in transfer setting. Uh, this is also an interesting thing. I haven't read this paper, but this looks like a good read. We work in a complementary setting where the entire model is kept, but some parameters are updated, so they're not pruning the model per se. The remarkable success of these works have sparked interest. The lottery ticket hypothesis, the conjecture that large language models are needed in pre-training only to induce in high probability the existing of subnetworks initialized with the correct inductive biases for training, and the finding that those past networks often transfer well to different tasks. So what this seems to imply is that large language models in pre-training create subnetworks within those models, and then those can be used for other tasks. So for bias terms and their importance are rarely discussed in literature. Zhao et al. Describe a masking-based fine-tuning method and explicitly mention ignoring the bias terms as handling them did not observe a positive effect on performance. An exception is the work of Wang et al., who analyzed bias terms from the perspective of attribution method. They demonstrate that the last layer bias values are responsible for the predicted class and propagate and propose a way to backpropagate their importance. Michael and Newbeck fine-tuned the biases of the output softmax in an NMT system to personalize the output vocabulary, and Frankel et al. Have demonstrated that randomly initialized CNNs achieve reasonable accuracy after training the batch norm layers alone. So finally, the closest is the work by Sai et al., which demonstrated bias-only fine-tuning similar to ours is effective also for adaptation of pre-trained computer vision models. Our work empirically shows the importance and power of this bias parameters to substantially change the network behavior, calling for further analysis and attention to bias terms. And the conclusion, they propose BitFit, a novel method for localized, fast fine-tuning of pre-trained transformer models for end tasks. The method focuses on fine-tuning on for fine on focuses the fine-tuning on a specific fraction of the model parameters, which are the biases. and they maintain good performance on the glue tasks. The focus on modifying a small group of parameters eases deployment as the vast majority of the parameters of the model are shared between various NLP tasks. It also allows for efficient hardware implementation that hardwire most of the network computation while the pre-trained with the pre-trained weights while only allowing for few changeable parts for inference. Besides its empirical utility, the remarkable effectiveness of bias-only fine-tuning raises intriguing questions on the fine-tuning dynamics and the relation between bias terms and transfer between language models and new tasks. And again, they thank the institutions which have funded their work. So in the appendix, let's just see if there's anything interesting. Okay, this is the naming notation. So this naming notation, if you ever print the Hugging Face parameters, the parameters get printed in this format. So they've named them like this. For training details, they've used initial learning rates for these, and bias experiments they use these initial learning rates, as the smaller rates took a long time to converge. With the larger learning rates, the bias only fine tuning converged in 8 of your epochs and up to 20 epochs on the others. They did not perform hyperparameter optimization beyond the minimal search over 4 learning rates. In each evaluation, they report x plus minus y, which is the result for training 5 models with 5 different seeds, and y is the standard deviation. To perform classification with Robota base, they followed above details but without hyperparameter search over the learning rates. For bias only fine tuning, they chose 1e minus 4, and for full fine tuning, they chose 1e minus 5 as the learning rate. As Mosbach et al. Show, fine tuning BERT large and BERT base, Robota base uh, unstable is unstable due to vanishing gradients. BitFit allows for the usage of bigger learning rates, and overall the optimization process is much more stable when compared to full fine-tuning. And finally, they describe the glue benchmark, but hope you're already familiar with this. So overall, this paper was really interesting. I really love such papers which are not very implementation heavy or uh, very difficult to say test on your own, and they give reasonable results, reasonable explanations, and good performance overall. So again, thank you everyone for tuning in for this video, and if you have any suggestions, leave them down below, and I'll catch you again with a new video hopefully soon.